Hello everyone, welcome. This is Rivas Kanal presenting Meme Fusion, our multimodal evaluation study on hate detection for Nepali memes. As part of the CHiPSAL 2026 share task, our team achieved a fourth place rank on Codabench by evaluating 8 model architectures against a highly complex, low resource dataset. Moving on to the next slide, motivation. Why focus on Nepali memes? Over 600 million people use Devanagari scripts, yet moderation tools primarily focus on English text. Memes fuse images and text, easily hiding hate speech from text only classifiers. Our goal was to find out which multimodal strategy actually works under these extreme constraints. Moving on to next slide, we have problem triple threat. We faced a triple threat. First, multimodal complexity. Neither image nor text alone reveals the full intent. Second, extreme data scarcity. With only about 850 training samples per fold, third, vision models like Clip are English centric, lacking the cultural context to understand the Venegari typography. On the fourth slide, we have task definition. The shared task has two parts. Subtask A is binary hate detection, which suffers from 2 to 1 class imbalance. Subtask B is 3 class sentiment analysis, where the neuter class is notoriously difficult. For both, our primary metric is macro F1, which penalizes models that exploit class imbalances. On the fifth slide, we have pretend encoders. For our foundation, we chose two powerful encoders. For text, we used BGE M3, fine tuning only the top layers to preserve its multilingual capabilities. For images, we used Clip VIT base, keeping the lower 10 layers completely frozen to prevent catastrophic overfitting on our small dataset. On the sixth slide, we have Ablation study to understand what works best. We tested 8 distinct configurations. These ranged from unimodal baselines to conventional early and late fusions, all the way to our proposed hybrid architecture M7, which leverages dynamic cross-modal attention to process original images and text. So, on the seventh slide, we proposed architecture M7. Here is M7. It projects both visual and textual embeddings into a shared latent space. It then uses a four-head self-attention mechanism to allow the image and text to mutually ground each other. For a learnable gating network weights modalities before classification. Moving on to eighth slide, the result of subtask A. On subtask A, M7 performed all baselines with a macro F1 of 0.6834. Noticeably, it beat our text-only baseline by nearly 6% and completely crushed the native early fusion by over 11%, proving that how you fuse modalities matters deeply. So, moving on to next slide, we have results of subtask B. For subtask B, the sentiment classification M7 again took the top spot. However, three class formulation proved much harder for all models, particularly the neutral class. Neutral instances lack the distinctive lexical markers found in clearly positive or negative posts, dropping scores by roughly 10 points. So, on the 10th slide, we have the accuracy F1 paradox. A critical finding was the accuracy F1 paradox. Our text only baseline achieved the highest raw accuracy, but only by aggressively exploiting the class imbalance and overpredicting hate. M7 had slightly lower accuracy but a significant better F1, preventing the massive over censorship of Beijing content. So moving on to 11th slide, we have error analysis. Where does M7 fail? Over half of our false positive occur when the model misinterprets political satire as genuine hate. Conversely, false negatives often happen due to cultural masking, where deeply local, code mixed political slangs flies entirely under the radar of our pretend encoders. On the 12th slide, we have systems under scarcity. Standard machine learning rules break down under extreme scarcity. Our bagging ensemble actually amplified noise because bootstrap folds overlap too much. Similarly, early concatenation failed due to the curse of dimensionality. There simply weren't enough samples to reliably train a 1500 dimensional input vector. On the 13th slide, we have limitations. we must acknowledge our limitations. We only had 854 training samples per fold, compounding a 22% OCR error rate. Furthermore, our dataset is heavily indexed on the 2022 to 2023 Nepali elections, meaning these models require careful cultural adaptation before being deployed elsewhere. So on the slide 14, we have our conclusion and future work. To conclude, dynamic fusion is essential for low resource multimodal tasks. Macro F1 must replace accuracy to prevent censorship, and English centric vision models and serious indic adaptation. Future work will be Future work will focus on synthetic data generation and integrating localized cultural knowledge bases. So, wrapping up with slide 15, we would like to thank you for your time. Our system secured fourth and fifth place rankings on Codabench for subtasks A and B. Our code and configurations are fully open source on GitHub. We would be happy to take any questions you might have on our methodology. Thank you, everyone. Wrapping this slide with Rivas Kanal from Department of Computer Science and Engineering, Kathmandu University.
Samir Wagli, Department of Computer Science and Engineering, Kathmandu University.
This is Abhil Adhikari from Department of Computer Science and Engineering, Kathmandu University. Thank you.
Thank you.